Hey everybody, welcome to episode 69 of the video series in which we program an entire video game from beginning to end in the C programming language. So today is a pretty interesting day. It's a red letter day because today I have decided that I would like to support Linux with this game. The reason why is because I know when we first set out, I explained that if you wanted to make a video game that most people are going to play, you're going to develop for Windows. What I mean by that, if you're going to develop a game that most desktop PC players are going to play, you're going to develop that on Windows. Despite Linux on the desktop having maybe 5% of the market, somehow every one of those 5%ers end up in the comment section of this channel and they all say, oh, where's the Linux support? How is this for Linux? Can I do this on Linux? So, I'm giving in basically, and I'm going to commit to making this game work in Linux. And for that to happen, lots of things are going to need to take place. It's going to take a lot of work because obviously I designed this game originally from the ground up to work on Windows, and everywhere where we touch the operating system, where we interact with the operating system, that's going to need to change. There are several components where that's going to need to change. I know that there are, I think, several times during the course of this video series that I've mentioned that we're not using any libraries in this project. And of course, that's not technically true. Anytime you interact with the operating system, you're going to end up using some sort of library, right? We're basically going to need to come up with, in as many instances as possible, we're going to need to use cross-platform libraries that have both Windows and Linux counterparts. That goes for our video, our audio, our Xbox gamepad controller stuff, and all those instances where we use libraries. If you go through main.c, I think where we no, it's main.h. Sorry, main.h where we include stuff. This is a library, obviously. X Audio library, that's Windows only, or Windows and Xbox only. X Input, that's Windows only. Sorry, here's the library, right? So we are using libraries. Obviously, little Windows multimedia library. There's another one. Oh, and the other interesting one, the one that we'll end up talking about today, actually, let's go back to main.c and go to the render frame graphics function. Scroll down here to this guy right here. Right, we call this once per frame, and we end up calling this. We do all this stuff to prepare our buffer with our image in it in every frame. We have like pixel perfect control over everything that happens in our buffer, but at some point we need to interface with the operating system and ask the OS, can you please paint this onto the screen for us? And what we're doing in Windows to do that is this stretch DI bits function is essentially the one point of contact we have with the operating system to get it to blit our buffer onto the screen, essentially. Needless to say, there's no such thing in Linux. So we're going to have to come up with some sort of cross-platform alternative that will give us essentially the same functionality as of that right there, but that has a library that has a cross-platform alternative opportunity capability. And I'll tell you right now, it's going to be OpenGL. But before we get into OpenGL, which that's what this episode is going to be about, by the way, is OpenGL. But before we get into that, we need to talk about some of the things that I've done off camera, some of the little things that I've done in between episodes, that I didn't want to bore you guys with. Basically, since last time, I created that configurable debug key, right? So you could have that debug text pop up when you hit the F1 key, or you could have it pop up when you hit the F2 key, or any other key that you may want. I realized that what I forgot was that all of the registry parameters need to go into a registry params struct that we already had available. I think if you go to main.h, you find, scroll down here to our registry params structure, all the way down here. Here it is, right? I can zoom in on that. I added another member here to debug key. They're all D words. You can see everything that we load from the registry is going to be in there. If I go to registry editor, I think I still have it pulled up here. I do. See all this kind of stuff. So if you set debug key, you can set it to whatever you want. By default, it's F1, but so for some people, F1 maybe isn't the best key for them. They might want to use another key, so that's how I let them do that. Which brings me to the next. I'll go ahead and delete these as I finish talking about them. Which brings me to the next item. I gave the load registry params function a makeover, and by that I'll just go ahead and jump over there. Load registry parameters. As you can see, currently only supports D words, and I made it much smaller by giving it the exact same treatment that we gave to the load assets thread maybe 1 or 2 episodes ago, where we created a new structure to represent the setting, the registry setting, and here it is. It's called reg setting, and it has a name. For each item in this array this array of data structures. Each registry value has a name. It has a destination of where in memory in our program it will go. It has a default value. This is what it will default to if the registry value is not found, so forth and so on. And then we open the registry key, and then of course right here we just simply loop through. We loop through everything, that data structure, that array of data structures, right? And we load them all. This is in contrast to the way that we had it before, where we just called, reg get value A this, reg get value A that, reg get value A this, reg get value A that, over and over again for everything that we had. This is just a slightly better iteration on the function, where this allows us to eliminate many lines of code from this function and put it all in a for loop. And let's go back to main.c. Let's go back up to the top. Now that we've talked about that, we talked about, here we go. We talked about load registry parameters. Okay, we remember last time we added a blit 32 bits per pixel bitmap buffer. We created an EX version of that function, right? Obviously, I did the exact same thing for the blit string function. I added an EX version of that function so that we could have all the same capabilities with our blit string function as we have with our new blit 32 BPB bitmap function, which is like alpha blending, and also the per color channel color adjustments and things of this nature. I'll show you what it looks like over here. Blit string to buffer EX, right? So I'll just click on that. String 1, blit string EX. Here we go. You've got your string, you've got your font sheet, you have your X and Y coordinates, you have your blue, green, red adjust, alpha adjust, and then flags. Very similar to what we did last time. It's the same, same idea. You also will notice that I took away the standard int.h types like I used to have in here. I can't remember, is it int fast? So, yeah, int fast 16t is what I was using. And then if you hover over this, of course, it's just a type def int. The more I think about it, the more I'm starting to my favor of the standard int.h data types is starting to wane. And the reason for that is I wasn't really gaining anything. Remember, I used to be using like an actual int16 here to specify that this was specifically a 16-bit value, which is actually just a short. Same, thing there. And here's what this was: this was a case of me performing premature optimization. I was essentially I caught wind of these standard int.h data types, the int 8 underscore t and int underscore or int 16 underscore t and all these kinds of things. And I was like, oh, well, maybe what I should start doing is I should start trying to economize my variables, right? By trying to make sure that my data types are as large as they need to be, but no larger. And in my mind, I was thinking, maybe if I have all of these things be 16-bit integers instead of 32-bit integers, that I would maybe be saving myself some, maybe I would be gaining a little tiny little smidgen of CPU performance by, maybe I could fit more values in CPU cache, and maybe the compiler could do some cool things where it could stuff more than one variable in a register at a time or something. I wasn't sure. Turns out, none of that's really true, and 99% of the time, you should just use ints, just plain old ints. So, what you're going to see me doing from now on is I'm probably going to start um, shying away from the standard int.h data types and just going back to these ints wherever it makes sense. Naturally, there are going to be exceptions to the rule. For example, let's take what is it, process player input, for example. Here you go, where we have G game input, and each one of these keys is represented by an int 16 t. Instead of making all those ints, I'm going to leave those as is or just make them shorts. I mean, it's a short. Short is a 16-bit integer. It's the same thing. The reason why is because I do want to maintain agreement between what this function is going to return and what and the variable that it gets assigned to, right? So if the function get async key state returns a short, then I want to make sure and assign it to a short as well. Um, that's just my current thinking. So again, I don't want to get too bogged down in it because again, it's just I feel like it's pedantic at this point. I feel like it's again premature optimization at this point. We're really fiddling with things that don't need to be fiddled with. It's not gaining us anything um, to really scrutinize. Should I use a 16-bit integer or a 32-bit integer here? It's not really an issue. The other type of exception would be like, you know, in my total frames rendered. Where do I find that total frames rendered? Obviously, this is going to be a 64-bit integer, and I'm going to leave it as a 64-bit integer because why not just make this a 64-bit integer and remove all doubt? Now you have until the age of the universe and your total frames rendered will never run out. It'll never wrap around. So that's another example of when we might not just use a regular, int. But enough about that. Let's go back to this blitzstring ex. Obviously, I added a couple things to blitzstring ex, which is like, I added a blit flag text shadow. You can pass on the alpha blending. Let's go ahead and look at blitzstring ex, which is blitzstring ex. Yeah, same stuff here that we've always had. Again, I've changed a lot of things to be just ints just because. Then we have, this. Here we go. I've got this bit of recursion in here, and again, I opted not to show you this because we've already done this. Back when I did the draw window episode, and we wanted to draw a window with like a thick border, we're using the same sort of recursion in here, where if I want to draw text with a shadow, I'm basically just drawing the text again recursively, but shifted down one pixel. And I thought about shifting it down one and to the right one, but the text, because of the way this font is, the font is so small, it doesn't look very good. It looks better if you just have it shifted down one pixel. I don't know, may play with that. But again, you can see that I'm using the enhanced extended version here, and I'm passing along the BGRA amounts, but to do the shadow, I'm taking away 192 from the alpha adjust. And then here, I'm using a bitwise operator to take away the shadow flag, because if we called this function again with the text shadow flag, that would of course lead to infinite recursion and Stack Overflow. So that's how that works, and here we go. So pretty easy, walk in the park there. We talked about blitzstring ex. We talked about blit flag text shadow, and now we what's the next thing? Reworked the opening splash screen to take advantage of alpha blending for smooth fade effect. And now, before I go on and explain it, let me just show it to you, and I'll hit go on this project, and here you want to watch carefully so that you can see the smooth fading effect that I added since last time. See, you saw the smooth fade out of the splash screen and then the smooth fade in of the main menu. Also, if you look very closely, you can see the shadow underneath the text now. Underneath all of these strings of text, there is a very subtle gray undertone, gray shadow underneath all of them. And I may play with that some more later to get the color just right. But it does add just a touch of, a nice finishing touch to have that shadow there. But again, like for example, if I hit the options menu right here, you see a really nice looking smooth fade in on that menu. Really nice looking smooth fade in there. Let's go back to, okay, how did I do that? Obviously, let's go to opening splash screen. First of all, basically I replaced this static text color because we're not using the old blit functions anymore. We're using the EX version of those functions. So I replaced those with an alpha adjust. Okay, and instead of adjusting the color per se, I'm adjusting simply the opaqueness to create that fade effect. And let's see down here. Yeah, it's as simple as this right here. Is like once we, this is on the splash screen, of course. Once we reach a certain frame in the splash screen, we just start subtracting from the alpha adjust, and that causes the fade out effect. Right, this alpha adjust -4 here, and then This gives us the capability to fade out the splash screen bitmap as well as the text. It allows us to fade those two things out in unison now, which before we did not have that capability. So, um, that's pretty interesting. Remember the text. If you go and open that bitmap, remember that it's actually the bitmap is black. The font is black on a transparent background. So if we want the text to appear white, we need to add these BGRA or blue, green, red amounts. We need to adjust them to 255, 255, 255 so that the text appears white. And then we use the alpha adjust to slowly fade it out. Similarly, if we go to, let's say, title screen, we have this bit right here that gives us a fade in. Now, if we have smooth menu fades enabled, then we do this nice smooth menu fade. If we like the old style better, where we wanted like a more like chunky fade in that is more reminiscent of what you might see on the old NES style, then we do that right there. And I define those things in main.h, obviously, way up here somewhere. Here you go, smooth fades, and also re-enable input after every X frames of delay. The reason I added that is because I feel like we were leaving the input disabled for too long after every frame transition, and it just didn't feel good. If you wanted to work the menus quickly, you had to wait for the input to be re-enabled, and it didn't feel good. So I wanted to re-enable the input more quickly after every scene transition or game state transition, if you will. But just to show you this, let me comment this out. Let me comment out the smooth menu fades, and then we'll see what they look like here. That one's still smooth, but the title screen, you can see it's back to the way it used to be, where it's sort of it steps in like it steps in like four 15 frame increments, right? So like 15 frames, you get 64 more alpha adjust, and then 15 more frames after that, you get 64 more alpha adjust, and then 15 frames later, you get 64 more alpha adjust. Um, Again, same issue, same thing with the option screen. So the functionality to have the sort of old school retro fade ins and fade outs is still there. But if we like the smooth ones better, then we can put the smooth ones in just with this pound define. And it's just a choice. We're gonna have to decide. It looks so cool to have these really smooth fades, and I'm not sure how cool it looks on your end, because on my screen we're doing 60 frames per second, but on the YouTube video as it's uploaded, I think it's only going to be 30 frames a second. But hopefully the effect comes through for you, and it looks pretty nice. It looks pretty nice on this end. So it's just sooner or later we'll just have to decide what we like better, the smooth ones or the chunkier fades that are more retro. Again, I didn't want to bore you with like all of the doing that manually, because we've kind of already done all that stuff. It's like if you're on episode 69 of this video series, you already knew all of the things that would have been required to do those things. So all right, we've talked about this, reworked opening splash screen to take advantage of alpha blending for smooth fade effects. That away. Don't know if we should adopt this for the entire game yet. Remember, we were originally going for an NES aesthetic, which didn't support alpha blending or smooth color gradients, but the smoother gradient looks so much prettier. So, don't know. Added a stop all game sounds function. This was simply because while I was testing hitting the escape key during the splash screen, I noticed that the sounds that were queued up wouldn't stop. The little lightning crashing sounds would continue playing even after you hit the title screen if you had skipped the cutscene. So I just added this stop all game sounds function to immediately stop all the sound effects that were going on. I'm sure we'll use that again at some point later on in the game. We already talked about the several instances of standard int types with, replacing it with just int in all of the areas where it makes sense. We already talked about that. And also now, since we're doing this fading, we're doing all of our fading, both the old school style fading and the new school style fading. We're doing both of those with the alpha channel now. That sort of renders the apply fade in function obsolete, which I am sort of sad to see that happen because the apply fade in function was brought to us by a GitHub contributor. And I don't want to, I hope there's no hard feelings. It's just the way this goes. You iterate and you iterate and you reiterate and you slowly make the code. You chisel away at it until it becomes the sculpture that you want it to be. I hope you aren't too hurt that we're going to retire the apply fade in function, but we are. Okay. Now we're going to talk about the real interesting part, the part that you came here to see, which is, remember, I said at the beginning of this episode, I want to start making this game compatible with both Windows and Linux, and maybe even Mac OS 2 one of these days. But in order to do that, several things are going to have to happen first. And like I mentioned before, at every point where we interface with the operating system, that's going to have to be replaced with some sort of cross-platform alternative, or at least, like, if deft to where, we can build it. If we do a Windows build, then it does this thing. And if we do a Linux build, then it does this other thing. But there are other areas where we can take advantage of cross-platform libraries. The first and foremost area where we can take advantage of cross-platform library is in our main render frame graphics function. So, as I mentioned before, I gave you a preview of what was to come at the beginning of this video. This stretch DI bits function, where we essentially take our frame buffer, if you will, our back buffer, and we send this to the operating system and we say, hey, paint this onto the screen. And this function does all of the work of stretching and rasterizing our tiny, like, 384 by 240 pixel sized back buffer. It stretches that onto your monitor, whether your monitor is like 1080p or 1440p or 4K or whatever it is. It'll stretch it out. This function will do that for us automatically. It's pretty cool, pretty handy function. Completely useless in Linux. This function does not exist in Linux. Can't use it. Linux does not have GDI. What Linux does have, however, is OpenGL. OpenGL is, and I'm not going to give you like all of the history of this, but it stems from like the 90s, state of the art 3D graphics from like the 90s. You think of like Silicon Graphics. They had these supremely expensive, $30,000 workstations that you could do all these 3D graphics things on. And, these guys, they were the pioneers of 3D graphics. And they created this library, the ancestor of what would become OpenGL. And so let me look at something here. Microsoft Windows does support, or I should say, they shipped support for OpenGL up to like version 1.1. The Windows operating system shipped supported OpenGL because obviously really cool 3D applications way back in the 90s were using OpenGL to do really neat things that had never been seen on a PC before, up until version like 1.1, which was like 1996, I believe. Yeah, like 19. I want to say 1996. You can go on Wikipedia and read the entire history of OpenGL if you want. But 1996 was when, around the time when Microsoft began developing their competitor to OpenGL, which was DirectX. OpenGL has evolved, and it's like on, I don't even know what the latest version of OpenGL is. It's a lot. It's much more than 1.1. But here's the point I'm trying to make is Windows, they no longer ship later versions of OpenGL now. Ever since Microsoft created their own competitor to OpenGL, which is DirectX, they no longer care about the newer versions of OpenGL, right? Um, that being said, I mean, any video card that you have is going to support newer versions of OpenGL, but you have to go and download the updated libraries and header files and stuff off the internet. So the cool thing is that if I want to use OpenGL 1.1 from 1996, that means every version of Windows has it. And it's probably safe to say that it's easily obtainable, if not already available, on any version of Linux out there that we may encounter. So OpenGL is going to be very amenable to our cross-platform journey here. What we're going to do in this episode, what we seek to do in this episode, is replace this highlighted chunk of code right here with OpenGL. So we're not going to be, this is obviously, a 2D game that we're doing all software rendering. And I am not proposing here that we do any sort of, this is a 2D game, and I'm not proposing that we are going to be doing any like 3D graphics. We're not going to be doing any 3D graphics here. What we're going to be doing is we're going to be using OpenGL to simply present our back buffer in the exact same way that we're doing here with these basically 3 lines of code, essentially. It's more than 3 lines of code, but it's um, it could be reduced to 3 lines of code if you had a really wide monitor. So OpenGL, let's go ahead and get into it. All right, so let's go to main.h where we start doing all these includes and stuff. I suppose in here somewhere we should probably define something here called OpenGL. OpenGL. Define OpenGL. If defined OpenGL, then include GL slash. And if you notice here, I have very little to choose from. These are the header files that come included with the Windows SDK, and you'll see that there's no like glue.h or glex.h, or there's like a lot more stuff that comes with modern versions of OpenGL that we simply do not have because we're only dealing with the really old version 1.1 version of OpenGL that shipped with Windows in 1996. Okay, so this is the 1996 version of OpenGL that we're going to be using. It's the very, very first version of it, or second version of it. very old, very primitive. It in no way represents the newer versions of OpenGL that have much more capabilities. But this has all we need in here, gl.h, right? That's all we need. And of course, we need to also include the library, which is uh, OpenGL32.lib. And again, you can count on this really old version of OpenGL existing on any Windows installation that essentially that has ever shipped since probably Windows 98 or at least Windows 2000, right? So the last 20 years, every Windows version that has shipped in the last 20 years has had this in it. So again, it's the only version included with the Windows operating system because Microsoft, they created their own competitor to OpenGL called DirectX, at which point they lost interest in OpenGL and began developing on DirectX only. So as far as I know, Microsoft no longer contributes to or cares about OpenGL, but we care about it tonight. So here's the thing with OpenGL. It basically consists of two parts. You have the part of OpenGL that interacts with the operating system. Like this is the part of OpenGL that you will be using to basically interacting with the operating system to get OpenGL up and running on your platform. That's the part that is going to vary between operating systems. So I'm going to have, and it's essentially the initialization layer. I'm going to have an initialize OpenGL function, and this initialize OpenGL function is going to have a Windows version and a Linux version, and maybe later on like a Mac OS version or something like this. That's the part that's going to differ. There's a whole other subset of OpenGL that is the platform independent part, meaning the part of OpenGL that code will compile the same regardless of whether I'm on the Windows platform or the Linux platform. So first, we're going to have to write this first part that I was just talking about, the initialization layer. And I don't know why it's telling me I got 395 errors here. I haven't really done anything. So perhaps I should have included this after like windows.h maybe. That would be my first guess. Right? OpenGL 1.1, like it's 1996. All right, let's try this again. Rebuild. Succeeded. Okay, that was it. All right, so now let's go to main.c. Let's go all the way back to WinMain. All right, so we're back in our WinMain function. And let's go down here somewhere. We got to pick some place where we want to initialize OpenGL. Let's do it. Okay, I think we need to do it before we create a window. So let me find create game window. Here it is. Create main game window. Before that takes place, I want to do if initialize OpenGL. Okay. And I'm going to go ahead and copy, paste, initialize OpenGL failed. failed to initialize OpenGL, and go to exit. Okay, now we need to actually build this function. So let me go to main.h and go down here to my function declarations, all the way down here. Here we go. Here we go. And we will make it return dword. Again, I'm going to have to even like get rid of the dword data type when I'm going when I'm migrating this to Linux, but we'll get there when we get there. For now, let's just create the function. Okay, back to main.c. Then we're going to create game window and make it right here. Again, as I was mentioning earlier, this is the part of OpenGL that is platform dependent. So I'm going to have to do something like that. I'm going to have to do an fdef, something like win32 else and if something like this. So this win32 constant, this switch right here is defined in Windows, both on 32-bit builds and 64-bit builds alike. So, you know, regardless of whether you're doing a 32-bit or 64-bit build, this essentially is going to be defined as long as you're using Visual Studio or Windows.h, right? I think that's how that works. Else, you know, this is going to be the Linux version. So our Linux version of initialize OpenGL will go here. Our Windows version of initialize OpenGL will go here. So first of all, we have, well, the way I like to start out all my functions. Okay. And then I have an exit label. And then at the very end of the function, I return result. That is not it. Return result. Boom. Okay. Okay, so the first thing is with when you're initializing OpenGL on Windows, uh, you know in Windows how you have a DC, a device context, and you, much like we did with our stretch DI bits function, it targets a specific DC or device context. Well, OpenGL on Windows has a very similar concept where it's basically layered on top of the concept of DCs, where you have a rendering context and you basically just target a specific DC or device context, and it's it's per thread. So if you call this function, if you initialize OpenGL on a specific thread, then it basically should just it should be relevant for this thread only. Like it's stored somewhere in thread thread local state, that any OpenGL rendering that occurs on this thread is going to be targeted at this specific rendering context. We'll get to that in a second. Let's do HDC. We do need to define, we need our good old-fashioned Windows DC here. Window DC equals get DC G game window. And now that I typed that, it reminds me that I actually need to go back to, this needs to have occurred. This needs to occur after we've created the game window. So let me go back to WinMain here. WinMain. Let me go back to create main game window. Right. This piece right here, initialize OpenGL. Let's cut. This needs to go after create main game window. You have to have already created the window before you initialize OpenGL to target that window. So, OpenGL is just like another layer on top of the whole device context thing that Windows has. The story will be different in Linux, but for now, this is tonight. This is just about Windows. Initialize OpenGL. Let's go back here. Okay, so now this is a valid thing to do because Game window has already happened. Now we need an HGLRC. This is our OpenGL render context. So we'll call it OpenGL render context. Okay, and now we need a pixel format descriptor. Well, let's do in pixel format index. We need a pixel format descriptor. Pixel format equals size of, and again, this is something that you see. This is ubiquitous within Windows, where need to you need to initialize the data structure with the size of the data structure itself as the first field. For some reason, Windows likes it that way. Several Windows APIs like it that way. Okay, so you have to perform this sort of dance where you ask the system. What we're going to do is here. I'm going to try to describe what we're about to do before we do it. We're going to fill out some information about the desired pixel format. I'm going to fill out this data structure and I'm going to tell it this is the kind of pixel format that we want. And then I'm going to send that to the OS. And the OS and the video card driver, they get together at some point and they decide, okay, here is the pixel format that we have that most closely resembles the pixel format that you requested. And if that pixel format tickles your fancy, then you can, roll with that. Since we have a pretty basic pixel format that we desire, we should be able to get it from the operating system. I think it's pretty safe to assume the OS will have the pixel format that we need because ours is pretty basic. But without further ado, let's go ahead and start filling this out. The version is version 1. The pixel format pixel type is PFD, which is pixel format descriptor underscore type underscore RGBA. That of course describes the order of our pixels in memory, right? Like that's, if you just look at raw memory, that's our, we're already doing RGBA pixels. These are 32 bit per pixel pixels, right? 8-bit red, 8-bit green, 8-bit blue, 8-bit alpha. Next we have pixel format dot EW flags. We have pixel format descriptor underscore support OpenGL, meaning yes, I actually do want you to support OpenGL. Draw to window, meaning like, yeah, I actually want you to draw to a window. And then PFD double buffer. Okay, so now the thing with the double buffer flag, we want double buffering, but I'm concerned about OBS. I don't know if OBS is going to be able to record the window with double buffering in place. So for now, let's comment this out and just leave it as a to do, because I think OBS may actually have an issue with OpenGL double buffering. It may just capture like a black screen But let's keep it moving. Pixel format color bits is 32 as far as I know. Pixel format dot C alpha bits equals 8. You can look these things up. It's all documented, although, I don't know how well it's documented, but here's the data structure. Pixel format descriptor. So C alpha bits specifies the number of alpha bit planes in each RGBA color buffer. Alpha bit planes are not supported. I'm not sure what that means. C color bits specifies the number of color bit planes in each color buffer. For RGBA pixel types, it is the size of the color buffer excluding the alpha bit planes. For color index pixels, it is the size of the color. Okay, for color index pixels, color index buffer. So, again, I'm not like 100% sure if this needs to be, because we have 24 bits of color plus 8 bits of alpha, which is 32 bits total. I'm not like 100% sure what that should be, so let's just roll with that for now and see what happens. I layer type equals PFD main plane. Hold on, what does that mean? I layer type. It is ignored. Earlier implementations of OpenGL use this member, but it is no longer. Okay, so it is irrelevant. It's ignored. Okay, so now pixel format index, which is our integer. It's an index. We need to use choose pixel format function, and we need to specify our device context, which is window DC, and then the address of our pixel format descriptor. So this is the part where we say by calling the choose pixel format function, we ask Windows, hey Windows, what pixel format do you have that most closely resembles this one, the one that we just specified? And then Windows will come back and say, well, here's what I have. Here's what I think. Here's the pixel format I think you should use. The one that most closely suits your needs. So if that happens to still equal 0, if pixel format index equals 0, that means we failed. Right? Because we can look up the choose pixel format function. What's the return value? If the function fails, the return value is 0. So sure enough, the result equals get last error and go to exit, right? Because we failed at that point. So assuming that choose pixel format was a success, then we are going to go on and use the describe pixel format function, specifying our window DC. We're going to specify the pixel format index, the one that we received from choose pixel format, and the bytes is going to be size of pixel format descriptor. And then lastly is, of course, we need the pointer to our pixel format. And this is where, okay, so what this function is going to do is we're reusing our pixel format descriptor data structure and just saying, I want you to go ahead and overwrite this with the correct pixel format descriptor based on the pixel format index that we got from Choose Pixel Format. Now, you see how you do this funny dance with Windows. I don't know, they designed all this stuff like 25 years ago. Set pixel format. Okay, now that we have our pixel format data structure completely filled out by the describe pixel format function, now we're going to set pixel format onto our window DC. And again, this is like a per thread operation, which is easy for us because we only have one thread in our application. Pixel format index, and then again pointer to our pixel format. Finally, we can use our open, which we didn't spell correctly, OpenGL render context. We get to use that now because we were finally about to set that up. Our OpenGL render context is going to be WGL create context window DC. Wiggle create context, and this wiggle prefix Windows GL, WGL, Windows GL, that's your hint to let you know that, hey, look, this only exists on Windows. Like, the way that we set this up is going to be different when we move to Linux. This is the platform dependent part of OpenGL setup. So we're doing the Windows part of it tonight. And so if OpenGL render context is null, then we're going to, of course, fail. We're going to exit, and we're going to do a wiggle create. We're almost done with this. Wiggle make current window DC OpenGL render context. So this is the part where we marry the Windows device context and the OpenGL render context together. We glue them together so that your operating system and your video card driver know that, hey, I'm going to start blasting stuff onto this window from, it's going to go to the video card and it's going to render onto this window. And again, we can go ahead and let's error check this. If wiggle make current window DC, if all of that equals false, then we report and exit. And one last thing we need to do. All right, so this is under our exit label. We need to go ahead and, if we have a window DC, we need to release it, right? Anytime you grab a window DC, you need to make sure and release it. So G game window and window DC. This is our cleanup, right? Okay, so there's one last thing I want to do, and since we're here, I want to take advantage of something that OpenGL is going to get us. OpenGL, DirectX can do this too, of course, but we're not using DirectX, we're using OpenGL. OpenGL gives us easy access to a specific capability that we have not had up until this point, which is another thing that makes this episode really interesting. This is going to give us access to VSync, vertical sync. Now, if you've ever played video games on PC, and if you're on episode 69 of this video series, you almost undoubtedly know what VSync is already. But if you don't, VSync is simply synchronizing the display of frames with the refresh rate of the monitor so that you don't have this situation where you refresh the monitor or refresh the frame rather during the middle of a monitor refresh. If you do, then you get these weird sort of like tearing effects on your screen. It's not something that we've been able to do with software, and you can sort of try to do it. I've tried to do it many times with like DWM, the desktop window manager in the Windows operating system. It has sort of like a VSync capability, at least it advertises that it does, but in my experience, it doesn't work very well. So I think we should go with the OpenGL implementation. And in order to do this, we basically need to use wiggle get proc address. So we've used get proc address before, right? To get the address of a specific function. This wiggle WGL version of it, it goes and finds this function, whichever function we're about to tell it to go find, in the OpenGL 32 DLL. And the reason why it's because this is like an extension method that, because we're using such an old version of OpenGL 1.1, this is the way that we have to get at this function. Just bear with me. This is how it works. The name of the function is wiggle swap interval ext. Right? That's the name of the function, and this function will help us. This is basically the function to enable VSync. All right, so we need to actually call this function. So let's go ahead and do the necessary. The function returns bool, and it's a function pointer. Trying to get all my parentheses here. When API integer, yeah. And we're going to pass it an argument of 1, missing a parenthesis. Right here. There we go. There we go. Okay, so I'm essentially going and finding this function name, and I'm calling that function with a parameter of 1, which means I'm telling my video card driver, hey, I want you to synchronize every frame. Before you display the frame, I want you to wait for a vertical refresh of the monitor so that every refresh of the frame is synchronized with the refresh rate of the monitor. And this, like for instance, my monitor is 144 hertz refresh rate. Most monitors out there are like 60 hertz refresh rate. It has nothing to do with like the 60 frames per second that we've already established to be, our sort of like established frame rate. So that's already separate from the refresh rate of our monitor. Those are two separate things. The thing that this function gets us is basically it interfaces with the hardware, the actual graphics card via our video card driver, and says, I want you to do this for me at the hardware level, which is something that we've not been able to do up until this point. So this will get us our VSync. At the same time, we're not going to do any error checking on this function because we don't want to fail. Even if this function were to fail, I don't want the whole game to fail, because who knows if the user may have like turned VSync off in their graphics card driver settings. We don't want that to prevent them from playing the game entirely, right? So we prefer VSync, but if VSync is not available, okay, we're going to let it slide. We're still going to allow you to play the game. So we've just done a lot of stuff here. So let's go ahead and run this and make sure everything still works. Looks like it's working. Okay, so we are done. I think we're done with our initialize OpenGL function. So now we can go to render frame graphics. We can go down here. So we are basically going to replace this call to stretch DI bits, which is Windows specific. It's GDI specific. We're going to replace that with something in OpenGL that is basically going to accomplish the exact same thing, but in a cross-platform manner. So let's do another ifdef OpenGL here. Else, and then end if under here. Okay. The first thing we need to do is set the viewport. So we're going to use the GL viewport function. And then let's just go read about it because I don't remember. We don't want to use OpenGL for reference because we're not using OpenGL for. Lower left corner. X is lower left. The default is 0, 0. Okay. The lower left corner of the screen, 0, 0. And then width and height. So our width and height is going to be like our game resolution width, which is 384 pixels, which again, the width of the viewport are set to the dimensions of that window. So I'm assuming this is in pixels. I mean, it's an integer, right? So I'm pretty sure it is. So let's just do performance data dot current scale factor, right? So that's our whole screen. Same thing with height. Game res height times G performance data dot current scale factor. Right, so now it should be starting from here. It's going to be blown out to. I don't think that's quite right yet, but we'll revisit that as necessary. Probably open up like Paint or something, because I really need to explain something conceptually. So here, OpenGL is, or historically was, all about drawing triangles. That's what OpenGL does, is it draws triangles. And in fact, the rate at which a graphics card was able to draw triangles used to be the way that people measured the effectiveness or the performance of a graphics card. Let's go to images.google.com. And let's look up 3DFX Voodoo 2 or something like this. Let's see, I'm looking for the box art specifically. These aren't really, let's try 3DFX Voodoo bots. Here we go. Here we go. We're getting there. Okay, this particular card is too small. Let's try this one. Okay, this one is good. This one is good. Okay, so like 16 or 17-year-old me goes into a store. I don't remember if it was Best Buy or Electronics Boutique or something like this, but this was back in the 1990s. And video cards this used to be the box art that was on a box that had a video card in it. And I'm pretty sure I owned this exact video card at some point. And the box art actually literally used to look like this. And if you can look right here, okay, it says 6 million triangles per second. That actually used to be, back in the 90s, used to be the way that people measured how good a video card was. Is like, this video card can do 6 million triangles per second. Well, this video card can draw 12 million triangles per second. By today's standards, that's not a good measure of how good a video card is. We don't really measure video cards by that metric anymore. But back in the day, back in the 90s, that used to be a very valid metric by which to measure the effectiveness of a video card, is by how many triangles per second that video card could draw. Okay, so I used to own this exact video card. I think I owned a few different ones of these. This is what video card boxes used to look like. Is back in the day, back in the 90s. This was back, these ones that fit into AGP slots back before PCI slots were even a thing, right? I used to own a few of these, not all of them, but at least a couple of them. All right, anyway, enough of that. So now that we know that OpenGL, drawing triangles is like the main thing that OpenGL does. So here's what we're going to do. Knowing that, this is our monitor, okay? This is our screen, okay? What we are going to do is we're going to draw two gigantic triangles all the way across our screen, like so, okay? And we're going to paint, well, here, so we're going to draw two gigantic triangles on our screen to encompass our entire screen. These two triangles are going to cover our entire screen. And, again, with OpenGL, you can sort of rotate them and tilt them, and, because OpenGL is designed to be a 3D thing, but we're not using it in a 3D way. We're using it in a two-dimensional way. We're going to draw these two triangles isometrically on our screen, and then we are going to map our back buffer, the back buffer that we already have, as a texture to go all the way across these two triangles. Okay, our back buffer, our memory back buffer that we draw all the pixels into, we're going to use that as a texture. And we're going to tell OpenGL that we want to map that back buffer as a texture onto these triangles. And in so doing, we will have created a exact replica of what we're doing right now with the stretch DI bits function, right? So I hope that gets the point across. Let's continue with this. I think what we need to do first is we need to do like a GL begin. So here we're feeding instructions to our video card, right? GL begin triangles. So we're telling the video card, hey, we're about to start drawing triangles. And for every GL begin, you need a GL end. And so all the good stuff, all your triangle stuff is going to go in between these two things. And so our first triangle is going to be GL, GL vertex 2D. Hold on. Well, we don't want the 2D version. This D means double. We don't want to supply a double. We want this 2I version so that we can supply ints and not doubles, right? Because as I mentioned earlier, when it comes to graphics on the computer, there's all sorts of coordinate systems you could use, right? Your origin might be in the bottom left of the screen, your origin might be in the center, you might be counting in pixels, or you might be counting in like 0.0 to 1.0 on the edge of your screen. You could be using lots of different coordinate systems, and OpenGL will allow you to use lots of different coordinate systems as long as you tell it which one you want to use. But in this case, we're going to go with 2i, which means we're giving it integers, and we're giving it a. Now we're going to specify vertices of this triangle, right? A triangle has 3 vertices, right? 3 points. And from these 3 points, you can draw the triangle. And using triangles, you can, if you draw enough triangles, you can make more complicated shapes, right? You can make, 2 triangles, you can make a square, you can make a rectangle. And if you have even more triangles, you can make parallelograms and hexagons and octagons. And then you can start like tilting them and making them look like 3-dimensional things. And, it basically, triangles are sort of the fundamental unit of OpenGL, which is kind of what I've said many times now. So let me just go ahead and go on here. I'm going to start this vertex at -1, -1. And again, like I said, the default state that OpenGL is in is going to have -1, -1 be the lower left, I'm pretty sure, lower left of the screen. So 0, 0 is the center of your screen. So -1, -1 is the lower left, 0, 0 is the center, and 1, 1 is going to be up in your upper right-hand corner. Pretty sure that's how it works. We're just going to have to see vertex 2i. The next vertex is going to be 1, 1, right? Single vertex 2i. And what's the third vertex? It's going to be -1 and 1. So going back to our example where we have our entire screen here, we've defined a vertex at, let's see if we can draw this intelligently. Paint red. Okay. -1, -1 right here. That looks bad. Let me do a circle. Okay, -1, -1 right there. The next vertex is 1 and 1, which is right up here. And the next vertex is -1 and 1, which I believe is there. -1 and 1. Or is it upper left? No. This is 1, 1. Okay? That's 1, 1 right there. Okay, so we are drawing a triangle from here to here. We're drawing this triangle right here, the bottom, basically the bottom half of the screen. That's the triangle we're drawing, right? by defining these 3 vertices. And I think, okay, I think that's all we need to do to draw a triangle. And I mean, you can make it have colors, you can do all sorts of things with it, but I'm just trying to get a triangle in there for right now. Now, hold on. We do still need this device context, so I'm going to pull this out from here, and I'm going to put this in here. And I'm going to pull this out of here, this release DC. I'm going to put it out here. Okay. So that now the only thing, instead of this stretch DI bits, we're doing this stuff right here. Okay. GL end. We have our device context at the ready. Now we just need to do swap buffers, which is the OpenGL way of saying, I want you to take the back buffer and I want you to make it the front buffer, right? We're swapping buffers. So whatever we had in memory, I want you to put it on the screen. And then, you can theoretically go and draw some more stuff in memory in your back buffer. And then when you call swap buffers again, it'll present it to the screen. And remember that because of our earlier call to whatever that swap function was that we used to call vsync, enable vsync, this swap buffers function is actually going to block until the next vsync, and it's going to do that with the precision in the precision given to us by our video card driver. Yeah, so let's go ahead and do that window DC. So we don't have to worry about like thread quantums and stuff like that. Things that we, hold on, that's device context, sorry. Things that we worried about when we were trying to measure, like get a steady 60 FPS in software. We don't have to worry about that with this here, because this is basically giving us it's interfacing directly with the hardware, which allows us to catch on to that VSync signal with more precision. So here's what I predict is what will happen is, now when we start this game, we should get just a white triangle covering the bottom right side of the screen. Just a white triangle. That's it. Let's run it and see what happens. Can we get nothing? 1 and -1, 1, 1. So I've gone back to my initialize function. I had to do a little bit of debugging there, and it turns out I need this double buffer flag in my pixel format descriptor. This is back in initialize OpenGL. So now if I go back to render frame graphics, all right, so hit that. Okay, and sure enough, I get a white rectangle along the bottom corner of my screen, which is good. Now, you can do some things here, like you can color the rectangle if you want to. What if I try it with GL color 3F and do floats instead of integers? Wonder if that makes a difference. It does make a difference. So now it's blue. The whole triangle is blue. Okay. Let's try to color the other vertices. Make this one 1, 0, 0. There we go. So we're trying to color each different vertice or vertex a different color. There we go. And you'll see that OpenGL does this really nice thing where it interpolates all the colors for you, and that's nice and cute. But we don't really need that. I just wanted to show you that it was possible. You can color, color from each vertex, and you can go on to try to like tilt them and do three-dimensional stuff like that. But we're not into that. We're doing, let's see, GL begin, bottom triangle. And then this is going to be top triangle. I can't spell anymore. It's getting way too late for me. And now this is going to be GL vertex 2I. -1, -1. -1, -1. -1 and 1. Okay, so that should be, now we're drawing a second triangle over the top left-hand side of the screen. Double check and see and make sure it works. And it does. We have a full square. Now you'll notice that we have a square. It starts, it covers up this entire left-hand side of the monitor, but it leaves this black bar over here. And if you recall, that is because we're not actually starting at 0, 0. Remember, our 384 by 240 pixel resolution is actually a 16:10 resolution, whereas my monitor, which is a 1440p monitor, is actually a 16:9 aspect ratio monitor. So I need to center it. So to center it, I need to do something like this: G performance data dot monitor info dot RC monitor dot right minus left. Hold up. Performance data dot monitor info dot RC monitor dot left divided by 2. And again, this is our generic formula for centering things, minus game res width times G performance data dot current scale factor divided by 2. Okay, and then this coordinate will be same thing but with height. Top minus bottom, right? Or bottom minus top. And that's the exact same thing that we had down here, right? I could have just copied and pasted what we had down here in our stretch DI bits call. It's the exact same coordinates, right? So let's run that and make sure that we now have a concentric rectangle within the bounds of our monitor, which we do, which is very nice. So now the next step is, and the final step is, we need to enable texture mapping onto these triangles so that we can map our background buffer as the texture to go onto these triangles. So to do that, I'm going to go, let's see, right after GL viewport, which is fine. We're going to do GL text image 2D, GL underscore texture underscore 2D 0. We're going to specify GL RGBA8 because that's the format that our pixels are in already in our back buffer in memory. We're going to specify the width and height of our back buffer, 0 BGRAEXT, GL unsigned byte. We're basically just telling it what the format of our pixels in memory, right? And then finally, here is the actual, here are our pixels, gbackbuffer.memory. That's basically, that is the texture that I want you to create. That's our texture in memory, is our back buffer. Okay, and then we need to set up like some stupid parameters for OpenGL, which is like GL text parameter I, GL texture 2D, GL texture min filter, GL nearest, GL text parameter. Did I even spell it right? Parameter I, GL texture 2D, GL texture mag filter, GL nearest, and GL text parameter I, GL texture 2D. And again, you can go and read the document. These are all documented. It's just setting up the parameters of, I'm telling it about the nature of our texture. It's a simple two-dimensional texture. And here's how I want you to, here's how I want you to treat this texture. GL texture wrap T. And I will go more into these parameters if we ever need to. But for now, I think it suffices to just get these down. GL text environment I, ENVI, GL texture ENV, GL texture ENV mode, GL modulate, and then finally GL enable, GL texture 2D. So all that crap was just to enable give us the ability to map a two-dimensional texture onto our triangles. All right, so now we're back into drawing our triangles, and we need to specify GL texture coord 2F. And I suppose these could be integers as well, but let's just do floats for now. This is just telling us where on the triangle should we start the texture, right? GL vertex, GL, we need to do another text coord 2F, and this is going to be 1.0 F 0.0F. One and one. I think that'll do. So this should draw, I'm only doing the bottom triangle right now, right? So let's run it and see what happens. So what has happened is we have a triangle on the bottom here that has our texture mapped onto it, but just the bottom right hand side of it. We still need to do the other half of the triangle here, or else we just have, you know, that's kind of a cool effect. But we need to do our top triangle, so let's do GL text forward 2F 0 0. GL text forward 2F 0 and 1. We're just making sure that the texture is just a straight, is maps all the way to the very edges of the triangle. And then finally GL text forward 2F 0 and 1, 0 and no, we already did 0 1. Hold on, I don't think that's right. 0 1. I think this should be 1 1. And this should be 0 0. Yeah, so I think that's it. All right, let's run this. There it is. Perfect. So now we are now using OpenGL to present our back buffer onto the screen. Again, we're not using OpenGL to render any 3D graphics. We're simply using OpenGL as a presentation mechanism. We're using it to present our pixels onto the screen. And the reason we're doing this is because it's cross-platform, and we can use the same code. We'll be able to reuse most of the same code on other platforms such as Linux and probably Mac OS as well. But there you have it. It's completely done. And again, you may or may not notice any difference in FPS, but we didn't really do this for the sake of hardware acceleration. We didn't really do any of this for the purposes of performance. We simply did this as a way to present our pixels onto the screen using OpenGL. So I'm not really concerned about whether we did or did not gain or lose any FPS. It's not really my concern with that right now. What I am concerned with is that it seems to work perfectly. There's no weird visual artifacts. Everything looks pixel perfect. Yeah, so that was a mega episode. That's OpenGL. We may or may not use OpenGL more in the future to do more interesting things. I don't know, but for right now, for tonight, we've used it to basically replace this right here. We did all this OpenGL stuff to replace this one call to stretch DI bits, but we did it for a good reason, and that good reason is that hopefully we'll be able to write more platform independent code using OpenGL later on. So with that, it's super late at night. It's way past my bedtime, so we're calling an end to this episode. So thank you very much for watching. If you have any questions or comments, please feel free to leave your questions and comments in the comments section. You can also find me on Twitter. It's all in the description of these videos. Please like and subscribe if you enjoyed what you saw tonight, and if you want to continue to see me develop these videos in the future. Don't forget there's a GitHub repository, again, in the description of the YouTube video. You can download all this code and follow along at home. That's all I have to say for tonight, guys. Again, thank you very much for watching. Please like and subscribe. And until next time, good night.